Thanks, Jeff. Okay. Hello out there. It's kind of bright here. Thanks, Jeff, for that nice presentation. First, I'd like to say how much I appreciate the Unitarian Universalist Society for inviting me to speak today on the science of climate change and provide an update on the critical issues surrounding that topic that is affecting us all. I'd especially like to thank Patricia Johnson, Crystal Gallagher, and Michael Galindo for handling the logistics, Glenna Sansone and many others for spreading the word around the talk for today, Kent Lechin for kindly offering to film the event, and the church and the Carmichael Colonists and several others for providing refreshments. So they should be back there. I'd like to give a special shout out to all the dedicated members of the huddle groups and environmental groups, and especially Mariloma High School students and their faculty members, Dean Karajanis and Joel Carson, for attending today's lecture. And last but not least, I'd like to thank my wife Cindy for holding down the fort while I researched all of the newest data for this talk. It's been a journey, believe me. If all goes well, I think we should be able to have an archived video copy of this presentation on my website within a couple of weeks. So things in the climate change arena have been happening fast, very fast. I woke up this morning checking my email to see what may have happened overnight, especially in Bonn, Germany, and we'll be talking a little bit more about that later. I update my presentations each time I give them, and it's harder and harder to do so because both scientifically and politically things are happening really fast, and I want to see how those two things interface. This is an extremely complex subject. What I'd like you to do, invite you to strap on your thinking caps and follow along for about the next hour as we discuss what issues are associated with this. There'll be a question and answer period at the end, so if you could hold your questions till then, that would be great. My goal is to provide you with tools to understand climate change and so that you can communicate with others in a more knowledgeable way about what some of the most recent issues are. There is a handout back there somewhere that will be a duplicate of a couple of my slides that I give on what we all can do, both individually, locally, as well as globally, to help resolve this issue. Electronics, especially you students over here from Mariloma, I know you're bound to your electronics. If everyone could turn off their cell phones, that way I won't get distracted. With that, let's go. If we could turn down the house lights, Crystal, especially that one in my eyes. Crystal, are you there? How about one more? There it goes. Nope, it's still there. I don't need the light on me. Much better. Thank you. Okay, I hope the clicker works now. Okay, so it's not working. Oh, man. Let's try to turn it on. Maybe that will help. Oh, that's better. Okay, so what is climate change? Let's start there on the basics. Climate change is not a hoax perpetrated by the Chinese. It is not a scam by scientists to get more research funding. And it is certainly not fake news, okay? What I would like you to do, if you take anything away from this talk today, is to understand that extreme variability is the norm now. And we are expecting let's cross that out. We are experiencing unpredictable and extreme weather events. And that is every day we hear something different about that on the news. No matter what news you read or see, it's happening. So let's discriminate between weather and climate. Weather is what you walk out of your house and you feel, whether it's raining, whether there's a tornado there, whether it's a heat wave, whatever, that's weather. But the changes in weather over time is what we term climate. And I'm going to hopefully show you things that relate to how we can measure that. So our world is changing, clearly. Temperature is up, rainfall is up and then down, unpredictable, snowpack is down and then up, fires are up, droughts are up, floods are up, tornadoes and hurricanes are increasing, sea level rise is up, El Nino events are increasing, seasonality is all messed up, and ocean productivity is unpredictable. So all of these things are consequences of and related to climate change. So let's start with the basics. If any of you have been through high school, some of you have, you probably have been exposed to the greenhouse effect, the natural greenhouse effect. Whoa, hello. Trying to figure out which button I'm using here. The natural greenhouse effect is over here, and basically the sun beats down on the Earth, and some of that heat from the sun is absorbed by the Earth, and much of it is returned back out to space. But because of some greenhouse gases, carbon dioxide, nitrous oxide, and methane, some of that heat is trapped by these heat-trapping gases. So with the human-enhanced greenhouse effect, here we have the same thing. The sun beats down on the Earth. Some of that heat is radiated back out into space, but we have more carbon dioxide, more methane, and more nitrous oxide. Because of that, more of the heat builds up in the lower atmosphere called the troposphere, about 7 miles high. So let's see what we have here. We've known about this heat-trapping gas for a really long time. And this little fellow here, Svante Arrhenius, in the middle, was the first person to actually write a model and describe the process by which carbon dioxide can heat the atmosphere. He did this in the 1800s. He actually got married in 1894. And for the next 2 years, he spent day and night, weekends, holidays, writing this model. And there's no computers back then, so it's all by hand. So at the end of the 2 years after he was married, his wife divorced him. I don't know what it is about these dedicated scientists, but that wasn't a good thing for him. Or maybe it was. He actually ended up winning the Nobel Prize. So I'd also like to show you another piece of information that indicates how we knew this stuff way back when. This is a news article from a newspaper in New Zealand in 1912, up here. And so I'm going to read it to you if you can't see it. The furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. That was 1912. We are feeling that effect now. Let's see if we can do that. Okay, the other thing that I'd like to start out with is the fact that 97% of the scientists agree, and it's up to 99% now, that global warming is happening. Not only that, but we are the cause, all right? There was a report that I'll tell you about in a little bit that just came out on Friday from the President, Executive Office of the President, that says global warming is real and we are the cause. So there's hope. So the way I like to frame this is scientists are the map makers. We provide the data, and you, the citizens, and the policymakers, and I put the policymakers in quotes here, are the navigators. We provide the information, and you guys, together with your policymakers, decide how to best protect our resources and human health. And that's basically the way it is, and that's the way it's going to stay. Let's see if I can get this thing to stay. And that's what we call science-based management. Provide the science and help the policymakers and the rule makers figure out how to manage based on true science. So what are the tools that we use to investigate climate change? We have modern evidence. We have things that we actually measure over the last 100, hang on. Over the last 150 years, we've been measuring global temperatures, tide gauges, atmospheric carbon dioxide concentrations, and altered phenologies like when the first buds come out, when the flowering times are, and when bird nesting and migration data take place. And then we have what are called proxies. These are prehistoric evidence that we gain from using other things that correlate with those parameters, such as oxygen isotopes in marine and freshwater animal shells, tree ring data, sediment core data, ice core data, and I'll be talking more about those as we move forward. So let's look at the greenhouse gases that affect us. Carbon dioxide is the biggest one. 82% of the influences from carbon dioxide. Methane holds about 10% of influence, nitrous oxide about 5%, and a bunch of different types of fluorinated gases are around 3%. We're going to focus our attention primarily on the biggest one, carbon dioxide, today. So here it is, carbon dioxide. 1 atom of carbon, 2 atoms of oxygen. You can't smell it, you can't taste it, you can't feel it, but it's there. It has mass, and actually it has a lot of mass. So where does carbon dioxide come from? Well, it comes from the burning of fossil fuels, from power plants, planes, trains, and automobiles. That's a really complex process right there. Won't have time to go into that. And all other types of combustion. And also, interestingly enough, cement production has a huge influence on the production of carbon dioxide. It's about 6%. So this is coming up here. Okay. Everybody that respires produces carbon dioxide through respiration. And so this woman here is respiring, but I would like to ask a favor. Everybody can really contribute to the slowing global warming by holding your breath during this presentation. And at the end, if you're still awake, we'll be talking of questions and answers. Okay, so you're all holding your breath now. I'll work forward from there. Where is that carbon dioxide going? Well, some of it's going into our atmosphere, and some of it's being taken up by plants through the process of photosynthesis down here, which you've all learned and memorized. So carbon dioxide plus water in the presence of sunlight produces sugars or carbohydrates and, of course, oxygen that we all need. So let's take a look at what's happening on both ends, both with the production end and the uptake end. So let's move on to the next important greenhouse gas. That's methane, about 10%. So here's Bessie, our favorite cow, and there's actually a clam over here too. And so Bessie does breathe just like you and I, and she produces carbon dioxide, and so does the clam produce carbon dioxide. But at the same time, Bessie and the clam actually produce methane. And Bessie's methane comes from, yeah, you guessed it, cow farts, but also comes from her burping. And actually 95% of the methane that's coming from cows is from their burping from the 4 stomachs that they had where bacterial fermentation is taking place. And actually the clams and worms in the marine systems also produce carbon dioxide, but they also produce methane as well. And they're contributing about 1% of the methane that we have in our atmosphere. And of course, Bessie also has some other things that produce methane and cow plops. So be careful out there, you don't want to get in the way of the methane. All right, so let's see what else we have here. There's about 1.5 billion cattle on the earth, and every one of those cattle produces about 25 to 100 gallons of methane a day per cow. And that accounts for about 28% of all the methane emissions there are, which for the total global greenhouse gases is about 3%. So let's start out with the measurement, the modern measurements of carbon dioxide. So a fellow named Ralph Keeling, right here, started in 1958 to measure carbon dioxide at the Mauna Loa Observatory at the volcano, 11,000 feet in the Big Island of Hawaii. And you see this graph here, and it has up and down, little red lines, and then it has a blue line. So the up and down red lines are the monthly averages for the carbon dioxide on Mauna Loa volcano. The blue line is basically an average of each one of those months, and he started in 1958, and it continued to go up and up and up and up, and until we get to where we are now, and that's about 412 parts per million. So we're going to be talking parts per million here. So let's take a look more carefully at what that up and down annual cycle means. So we have this annual cycle. Here it is. In the northern hemisphere, the carbon dioxide is going up, up, up towards the spring, April, May, and all of a sudden it starts going down. Well, what happens in the spring? We have leaves coming out on the trees. They are sucking up carbon dioxide out of the atmosphere. And they continue all the way through the summer down to the fall, when what happens? They fall off the trees, and there's not none, but there's much less photosynthesis, much less carbon dioxide being sucked up, and the carbon dioxide starts going up because we are producing carbon dioxide, which is going into the atmosphere. So this is just a little primer on what's happening with carbon dioxide. So let's see what else we have going on here. So here's that same curve, the Charles Keeling curve right here, about 50 years worth. So we're going to squeeze that down here and look at the last 1,000 years of carbon dioxide concentrations. We're up here at 412. We started in the last 1,000 years at about 280 parts per million. Each one of these little dots is data from an ice core. These are some of the proxies that I was mentioning earlier. So we see that's going there, and what's happened is at the start of the Industrial Revolution, when we started burning fossil fuels, that curve started going up and up and up, and it's going exponential all the way up to where we are now. And it's sort of curved like this, kind of looking like a hockey stick, and some people call it the hockey stick curve of increasing carbon dioxide. So here's that curve right there, the one we just saw with 412 parts per million, and there's the Industrial Revolution. Now let's look back, instead of 1,000 years, let's look back 400,000 years during the Ice Age period. So when there was lower concentrations of carbon dioxide, down around 200 parts per million, we had much more ice, glacial situation. When we had higher concentrations of carbon dioxide, we had less ice. So more ice, less ice. We've gone through these 4 Ice Age cycles, and humans sort of entered the stage about 200,000 years ago. And we weren't very influential at that time in controlling carbon dioxide, that is. And here's our Industrial Revolution over here. So we might have been coming out of an ice age and maybe going back into one, but instead of going down again like all these other ones, we're going straight up and up and up and up, exponentially higher. So this is looking back in time just to see what it looked like back then. So there are thousands and thousands of scientists working on this problem. And the Intergovernmental Panel on Climate Change, the IPCC, produces these assessment reports about every 5 to 7 years. And this one was a multi-volume report in 2013, 2014. And here's a summary synthesis report that is typical of their productions. And these are quite readable if you look them up on the internet. The next one we're expecting is in 2018. So I'm sure there'll be announcements of that, and you can actually pull that down. So interestingly enough, 2 days ago, there's also special reports that come out on climate. And this one was a climate science special report put out by the U.S. Global Change Research Program, which has now put out its 4th volume on Friday. So we're pretty clear. I have a number of different data points in my presentation from this report. And it's composed of scientists from 13 federal departments and federal agencies. And it's overseen by the Executive Office of the President. And it's interesting that it came out because the results indicate, as I mentioned earlier, that climate change is real and it's human-caused, approved by the Executive Office of the President. So we'll be talking about some of these other things a little while later. Notice here, this is a satellite picture of a atmospheric river coming over from the tropics, from Hawaii area, right into Southern California. Excuse me. Let me take a little drink. And we're going to see more about these atmospheric rivers in a bit. So this is a good time to introduce the concept of attribution. Individual events like hurricanes or heat waves or tornadoes or any kind of major weather event cannot be really ascribed to climate change. However, when we look at the frequency of those events, the intensity of the events, timing of the events, all these things under long-term changes, then we can ascribe more information to that as being related to climate change, especially if we know what the drivers are for climate change. And this is one slide here. This is a compilation of many, many different studies and factors, but basically all I want you to take from this is from that report that I just mentioned, that the relative contribution of human-caused climate change is huge. Solar radiation is not causing it. Volcanic activity is actually cooling the Earth, not heating it. So this is what one of the conclusions of that report are, that humans are vastly overwhelming the natural processes and the natural cycles on the Earth. So the global community, all the countries of the world, have been emitting about 100 million tons of carbon dioxide each day into our atmosphere. Fossil fuel emissions account for about 94% of those, and they're contributed by coal. About 42% of it is coal, 33% oil, natural gas, 19%, and again, the cement plants are contributing a significant amount. Also changes in land use. When the forests are chopped down to grow cattle to make hamburgers, that is deforestation, and that prevents those forests from taking up carbon dioxide out of the atmosphere, so we lose some there. All of those processes are active. Well, coal has been declining actually for the last 15 to 20 years, and the reasons are, number one, the lower cost of natural gas, the alternative renewable energy sources that are being developed, and the regulations to protect human health. And what's interesting is that California has 10 times more jobs, about over 500,000 jobs in the alternative energy field than the entire US has in coal jobs, about 50,000 jobs. So coal is on the downturn and probably isn't the best option simply because of economics, if nothing else. So President Obama put forward in 2015 the Clean Power Plan. Sorry. Trying to teach you there. No. Clean Power Plan, which basically was a plan to limit greenhouse gas emissions from existing power plants, both primarily coal, which would reduce our nation's carbon emissions by 1/3 by the year 2030. That was 2015. However, this is the EPA Administrator, the Honorable Scott Pruitt. On October 10th, the Honorable Scott Pruitt submitted a 43-page proposal to repeal Obama's Clean Power Plan, allowing power plants to use any fossil fuels they chose, including coal. On October 23rd, the Honorable Scott Pruitt prevented 2 climate change scientists from presenting the results of their studies on climate change impacts on Narragansett Bay in Rhode Island that were funded by the EPA. And you probably heard about this. On October 31st, last week, the Honorable Scott Pruitt blocked any scientists who have been funded by the EPA from serving on EPA science advisory panels. So this is what I would call not science-based management. We need to have science involved in the management process, and I have to say this is not doing it. So let's look at who's emitting most of the carbon dioxide. So as of 2014, 2015, by country, the United States was going along here being the top producer of carbon dioxide for quite a while, until 2004, when China passed us out pretty significantly, and China is just keep going up and up and up as they ramp up their economy. Below the United States was the European Union, and below that is the Russian Federation, India, and the last one on the bottom is Japan. This is only 5 or 6 countries out of the 194 countries that are in the world. But the top 10 countries are producing 2/3 of all the global gas emissions. So that's by country. Let's take a look at it by per capita. So for each person on the Earth in these different countries, thanks. The United States is doing a good job. It's producing the most amount of carbon dioxide per person with our lavish lifestyle. The European Union is next, and this is a global average. But here's China way down here. Interesting. Well, China is producing so little per person, because they have so many people that the carbon dioxide that's being produced is diluted by all that high population number. And then India is down here. So just keep in mind, you are here, okay? Tons per person. Each one of you is producing about 15 tons of carbon dioxide per year. Are you still holding your breath? All right, carbon dioxide and temperature. Let's take a look at temperature. So as carbon dioxide increases with this white curve going up here over time, it's from 1880, just around the time of the Industrial Revolution beginning, up to 2016. This last year, we've reached now, I said, 412 parts per million. Temperature on the left in this blue line is variable, quite variable. However, it's going up in accordance with the carbon dioxide. So there's a clear relationship between those because of carbon dioxide being a heat-trapping gas, which we've known for over a century. This is the problem that we're facing. How do we solve this? Get the right button here. So the last time CO2 concentrations were this high at 412 parts per million, humans did not even exist. That was 800,000 years to 20 million years ago. Global temperatures were substantially higher. There was almost no ice on the planet, and sea level was 100 feet higher than it is now. So here's just a peek at the 1,700-year record. This is where we are now, way up here in carbon dioxide. And this is what carbon dioxide was doing. I'm sorry, wrong parameter. This is temperature. So as temperature has varied over the last 1,700 years, it's been variable, up and down, until we started into the Industrial Revolution, in which case it is now exponentially higher, and it has exceeded the temperatures in the last, actually, 20 million years. So how hot is hot? The last 10 years, all since 1998, these are the years that were increasing and increasing up to 2016. We don't have 2017 yet, but we're going to get there fast. This increase in the temperature for the globe makes 39 straight years of above average global temperatures and annual temperatures. And, hello, come on. The odds of that happening randomly without global warming is 1 in 27 million. If you're a statistician, that means something to you. Even if you're not a statistician, that should mean something to you. Okay, let's take a look. So 2010 was a record hot year. 2014 exceeded that, was the hottest year. 2015 exceeded 2014, and 2016 was the hottest year past that. Every single year now, we're getting the hottest global temperatures ever. And 16 out of the top 17 hottest years have been since the year 2000, and since there's only 17 years in that time period, we're in trouble. So, record highs. This is this past summer, a few months ago. We're breaking hundreds of temperature records throughout the United States, especially in the West. The West has suffered the most in all of this. I just turned it off. Okay, good. And 2017 was the most intense Southwest heat ever recorded so early in the season. And what's happening here is we're getting all this extreme weather of all types, all at the same time. We've got severe drought in the West, a heat wave affecting the temperature and humidity. We've got severe storms in the Midwest, and we've got torrential rain from tornadoes and hurricanes coming, and here's the tropical storm Cindy coming up through the Gulf of Mexico. Well, I know something about tropical hurricanes and tropical storms. My wife's name is Cindy, and we have lots of those tropical storms at home. So I know something about tropical storms. I'm sorry, where are you? I guess I'll be staying here for the night. Heat content, where is all this heat going? It's going to the ocean primarily. Upper ocean has a huge amount of heat stored in it from carbon dioxide. Deep ocean has a fair amount. The ice actually holds some of the heat. The land holds some of the heat, and you can't probably see it, but there's a little tiny black rim down here at the air. So there's some heat held in the air. But primarily it's 92% of all the heat is being stored in the ocean. So let's get a little closer to home right now. These are some model runs that were done by a U.S. Geological Survey scientist, Mike Dettinger, and he's done this for Northern California for both temperature and for precipitation. Let's look at for the projections of temperature starting where we are now, 2017, up to the year 2100. 2100 is a year where most scientists are projecting and predicting what will happen in terms of global climate change. So what we see here is that he ran 23 models, all using these different assumptions about how much carbon emissions are being produced in different years. And what he found was that 20 out of the 23 were in this range right here, between 3 and 6 degree temperature increase over that time period up to the year 2100. So what that tells us is that, and that centigrade temperature is 5 to 11 degrees Fahrenheit increase in Northern California. That's a strong consensus for warming, clearly. So let's take a look at the precipitation part down here. He did the same thing. Here's 2017. And he ran his models again, 23 models, and 19 of the 23 were in this range right here, about half of them above zero and about half of them below zero, indicating that we probably don't have much certainty with respect to whether we're going to get more precipitation or less precipitation as we move towards the year 2100. It could be variable, it could be extreme, but we're not going in any one particular direction. And we'll talk a little bit more about that as well. So here's the global temperature taken at many different locations. Each one of these different colored lines is the global temperature from 12,000 years ago up to the present. So if we look at this, the black line, the heavy line, is an average of those temperature readings around the Earth. So back in, here we are, come on, you can do it. There we go. About 9,000 years ago, humans started agriculture, all right? Developing crops. About 4,000 years ago, we started developing cities and aggregations of communities and civilizations. During this entire time period, all of that was being done within a range of about half a degree centigrade. So everything that we've known throughout most of modern human existence is within a half a degree centigrade up or down. We've developed our crops, we've developed our health issues within that period of time, understanding what to do with increased temperatures. Now we're projecting 5 to 11 degrees Fahrenheit above where we are now, which is, we're going to have to do some adjusting there in terms of how we deal with all of these factors in life. Now I'm going to try a tricky thing here. I want to show you, I'm supposed to be able to, there's the mouse, whoa. Up, there we go. Bear with me. Oh. Come on, I can make this work. All right. So what I wanted to show you is that temperature is not the same all over the Earth. And as we look at the dark lines here, the dark colors, these are cooler temperatures, these are warmer temperatures, and you can see that there's lots of areas where the Earth is cooling at some times, in some places, warming in other places over time. So we're in the 1940s, 1950s, moving on to the 1960s. Earth is adjusting with its temperature budget, its heat budget. 70s, 1980s, 1990s, and the 2000s, 2006. So pretty obvious, just visually, most of the heat is changing and the greatest in the Arctic, up in here. And we are indeed losing much of the ice caps in the Arctic. So let's move beyond that. We'll come back to the Arctic in a second. Precipitation, extremes of precipitation, either up or down. For instance, the hurricanes that we've just seen this hurricane season, Hurricane Harvey, Category 5. There's Houston up there. This is the coast of Texas. Hurricane Irma, Category 5. Hurricane Irma, and then Jose right behind it, Category 4. And Hurricane Maria, Category 5, just slammed Puerto Rico. We have people evacuating Puerto Rico because they can't survive there, which is going to happen as we move forward with climate change and mass migrations as well. So let's look back. Throughout the 1970s and 1980s and 90s, this is a graph that shows total number of hurricanes in the blue bars, maybe 4 to 5 hurricanes during that period up to the 1990s. And Category 3 plus hurricanes are in the yellow, so maybe Category 1 or 2. Now as we move into the 1990s, into the 2000s, we have hurricanes increasing in frequency up to 7 or 8 per season, and maybe 4 or 5 of them, 4 I guess, that are plus Category 3 or larger. Let's take a look at what's happening this year. We have already 10 hurricanes, 5 of which are Category 3 plus. So if this is any indication what's going to happen through the rest of this time period, it's clearly increasing and clearly getting more devastating, both with respect to human health as well as economically. So we'll have to wait and see what happens with the rest of this season. This hurricane season is not over till the end of this month, so we'll see if we get any more. And that process, I mean, that 10 hurricanes has not happened since 1893. This is a track of the hurricanes this 2017 season. What's happening is that the hurricanes are starting further and further east in the Atlantic. And this last one, Hurricane Ophelia, started here in the mid-Atlantic, and then it went east instead of going west, and went right through Ireland. And you probably read about the devastation that it caused in Ireland. This is the worst storm they've had ever in Ireland. And the strongest hurricane ever was along the Mexican coast in 2015, and it had 200 plus mile an hour sustained winds and up to 235 mile an hour gusts. Extremes, very, very clear extremes. Okay, here's the atmospheric rivers I talked about earlier. Atmospheric rivers are basically the Pineapple Express that the weatherman talks about. They're about 250 miles wide, a mile high, and they carry huge amounts of moisture from the tropics into the coast of California. And there was a superstorm in 2010, 5 days long, and it dumped about 26 inches of rain in coastal California and 17 feet of snow in the Sierra Nevada. So here's the ticker right here for the days of the 5 days, and it keeps repeating itself. So here's Hawaii right here. This massive amount of moisture is coming in and hitting Southern California. Unfortunately, most of the large reservoirs are in Northern California, not Southern California, and most of that goes back out to the sea. And in our drought, we're not able to capture that when that happens in such massive amounts all of a sudden. So those are atmospheric rivers, which are apparently coming more often. Okay, looking at the U.S. Drought Monitor from University of Nevada at Las Vegas, you can see here the darker colors are the more severe droughts, and the West is really plagued with these massive, massive droughts for several years at a time. We're still not out of our drought. It's about 5 years now. But let's take a closer look at California. So here's a closer look at California. We have these categories of dryness and drought. And this last one, D4, exceptional drought, I was told they had to make a new color to describe and represent the level of drought that is occurring in California during this last drought season. And here's a shot of the snow drought, which happens because we don't have much precipitation as well. So in the year 2015, this is the amount of snow they had up at one place in the Sierra Nevada. They go there every single year on April 1st, And this is the person from DWR, Department of Water Resources. Here's Jerry Brown. No snow that year. This is 2015. The year before that, this is 2014, they had this amount of snow, not very much. However, and you can see that the amount of snow is declining over the years. They're highly variable, but the amount of snow is declining and declining, especially these last 4 years here. So looking at 2016 was way up, just the opposite. And 2017 was massive. In fact, it's so massive, it went up 183% of the snow from normal average. So again, precipitation and the snow that's occurring as a result of precipitation is not predictable. It's either extreme up or extreme down. So again, modeling helps. Throughout this drought, the farmers in San Joaquin Valley have been pumping groundwater to supply the water for their crops. And this has been going on for decades, but especially now since we've reached the drought category, the drought years. And because of that, they're pumping out of these geologic formations that have water in them, many of them because they're clay-like, they collapse, and once they're collapsed, you cannot refill them from rainwater. There are some places in California where they're finding more larger grained formations where they think they can recharge the water table, but down here, they're not doing that. So what's happened is the San Joaquin Valley floor is sinking about 2 inches per month, and the farmers are pumping groundwater during this extended drought. Now let's take a closer look at that. Here's a picture that sort of represents it. Originally, 1925, the ground level was up there. 1955, the ground level was there. 1977, the ground level is there. And that's not a little toy soldier, that's a real person down there, 6 foot high. And this has been occurring in San Joaquin Valley over 5,200 square miles, and as much as 28 feet of the land has subsided. And that's right now, we're looking at a foot a year in some of those places. Now, it's not happening everywhere, but it is happening in much of the San Joaquin Valley, and especially along the I-5 corridor. The dark areas, again, are the areas that are subsiding the most. Not everywhere, but most of those areas. These are the agricultural fields along I-5. So as you dry things out, lower humidity, we get beautiful sunsets, yeah, but that's about the only positive thing I can say. This is the interactive wildfire tracker from Climate Central, a very good tool. Each one of these little fire icons has information in it. You click on this online, and it gives you all the statistics, how much acreage is being burned, how many structures are gone, how much containment they have. And this is from August 2016, last summer. And you can see, and you know that it was burning up last summer. It's also burning up this summer. But what you probably didn't realize is that Alaska had even worse conditions in burning during the summer of 2016. So this is becoming the norm now, these fires. As we go on from 1970 to 2015, we have increased frequency of fires, and this is the one that you probably remember just a few weeks ago, the 6 complex fires from Napa and Sonoma burned for 4 days, 170,000 acres, 8,900 structures, 42 deaths as of about a week ago. And I think you probably all remember this before and after picture of Coffey Park in Santa Rosa. We know people who have lost their homes there and other fires up north. So you probably do as well. I don't need to go over that. So let's get a little wetter here. SLR, it's not single lens reflex. It's actually, what is it? Oh, I can't remember. Oh, I guess it's sea level rise. Okay. We're going to talk about some things associated with sea level rise. I'm going to leave that one there. Sea level rise is caused by a whole suite of different kinds of factors, which we don't have time to go over today. However, about 50% of the sea level rise is caused from the melting of glaciers and the ice caps. About 50% of it comes from seawater expansion. You might not think about seawater expanding that much, but it actually does, and it's 50% of the sea level rise. and another 50%, no, that's not right. Never mind. Let's take a look at what's happening with that Arctic sea ice. This is a shot in 1984, a satellite shot of what the extent of the sea ice was in September. And in 2016, visually you can just see how much less sea ice there is in the Arctic. And looking at a graph, it's declining all the way down to 2015. That's the Arctic. And let's go to the other pole, the Antarctic. We have not only sea ice, but we also have land ice. Most of the Antarctic continent is covered with ice. And recently, you may have heard of this, the Larsen C ice shelf broke off. And for quite a while, the NASA's Ice Bridge mission has been following this 100-mile long crack in the, and there it is, a picture of it from the air. And here it is, another satellite photo. And this crack has formed in this shelf, this sea ice shelf. And as of January 2017, this is where it was. And watch it closely, it's moving. There, on July 12th, 2017, an entire structure broke off. And now there's an iceberg the size of Delaware floating around in the Antarctic Sea. So not only did the Larsen C ice shelf break off, but before that, the Larsen B ice shelf broke apart several years ago. And before that, the Larsen A ice shelf broke off before that. So I would say the frequency and progression of this is probably indicative of climate change because everything else is melting down there. So just be aware of these things happening, not just in our neighborhood, but around the world. So I was lucky enough to get down to Antarctica this year and found 7 different species of penguins. Some of them are having a hard time. This is a king penguin colony, about 500,000 penguins. This is adults. Here's a little chick over here, little chick. And unfortunately, some of the cold-adapted penguins are being outcompeted by the warm-adapted penguins because the temperature is rising so much. In addition to that, almost all of the species of penguins feed on krill, these little crustaceans in the ocean. And unfortunately, 90% of the krill are now dying off because of warm water on the ocean surface in Antarctica. So they're having a hard time. This is really affecting the coldest areas on Earth. So let's bring it back home, a little closer to home. The National Research Council in 2012 did a study comparing Washington, Oregon, and California in terms of estimating the future sea level rise up to the year 2100. So let's take a look at that. For the year 2030, we have estimate for California. This is the sort of the baby poop colored bars here. 0.8 feet is expected. We don't have babies anymore, so I can say that. By 2050, California's sea level rise is expected to be up to about 60 centimeters or 2 feet. And for 2100, here's California again, sea level rise is expected to be up to about 5 feet. So look for your oceanfront properties coming in closer and closer here. Okay, that's California. Out in the Pacific, we have many atolls, which by nature of the way they were formed, are pretty much only 6 feet high. So many of those atolls are have populations on them, and the island nations are getting worried. Some of them are already being affected, and they're trying to figure out ways to handle this. So unless you've overbuilt your population, your atoll, you're probably going to need some help. So here's the number of different island nations that are already making plans. The Carteret Islands have about 2,000 people in their islands, and they've made a plan to move their populations over to Papua New Guinea. Tuvalu has about 10,000 residents, and they've made plans to move their populations down to New Zealand. The Kiribati, with 110,000 people, have negotiated with Fiji to occupy some of their islands that are higher, not atolls, but higher. And actually the Shishmaref Alaskan Eskimos are on land. Their villages are on land, but because the villages were protected by sea ice from storms, the sea ice is now melting, or melted already, and those storms are coming in and wiping out their village because there's no more protection from sea ice. So all of these island nations, or even closer nations, are having to make plans to move out or be severely impacted. So now let's get even a little closer to home. I wanted to show you that the ocean is not the same height everywhere. So if we look here, here's Seattle. Puget Sound is about 8 foot higher than we are down here in Southern California. And in the Bay Area, the South Bay is about 4 foot higher than Suisun Bay. So let's take a look at what's there. Here's Route 101. This is in the South Bay. Here's Palo Alto up here. Here's the bay. And I'd like to show you what would happen in the case of a 100-year storm surge. So the waves are going to come in, high waves will come in, and just watch the result. This is where the bay would end up, is right in here from where it is now, just with a 100-year storm surge, no sea level rise. So if we add a 50 centimeter sea level rise to this, we would be out here by this light blue rim. 100 centimeter sea level rise would be out in the yellow, and a 150 centimeter sea level rise would bring it out to this red area. So let's take a look at who's out there. This is all Silicon Valley, remember. We've got Inuits, the Eskimos. Intuit, Google, Yahoo, Dell, Intel, all these great companies that you know and love. Looks like they would be impacted by this. So I can see you probably can't see me, but how many people own, take a poll here, how many people own iPhones, iPads, iPods, or use an Apple computer? Good, okay. So I'm going to show you the next slide. All right, so this, you're good, because this is Apple's Cupertino headquarters right down there. They're safe, all right? And I thank you for using Apple products. My son works for Apple, okay? All right, upwelling in El Nino. Hello. Okay, there was some guy who said the coldest winter I ever saw was the summer I spent in San Francisco. I don't know who that was, but, oh, there he is, Mark Twain. Why did he say that? Because it's cold. And why is it cold? Wind, fog. Wind and fog, that's correct. Why would it be the wind and fog in the summertime of all times? Well, that wind and fog actually supports an entire redwood community out here and all the species that exist in there. If there wasn't that wind and fog, you wouldn't have this rich forest and all the species that live there. So let's find out why we have that in San Francisco. We have it because of a process called upwelling. From about April through August, we have northerly winds blowing down the coast. And because of two processes, one is the Earth spinning on its axis, and the other one is called the Coriolis effect, what happens is, if this is our coast, the winds are blowing down this way, and what happens is it moves that surface water out to sea. It pushes it off to sea. Now there's a void here in the water. We need to fill that void with something. So we have deep, deep water, 1,000 to 2,000 feet, coming up to the surface, upwelling, and that water is cold, and when it hits the warm air, boom, we get fog. But in addition to the fog, that water is nutrient rich. And when we bring that nutrient rich to the surface, it supplies food for microscopic plants called phytoplankton, which feed microscopic animals called zooplankton, which feed small fish, which feed large fish, and which feeds marine birds and mammals. And so we end up with a very rich and productive marine community. What happens when we have an El Nino event is we have a crash, because the El Nino event slows those or eliminates those winds coming down the coast, which eliminates the upwelling, which eliminates the nutrient-rich water, and then the entire food web collapses. So we don't have any reproduction for marine birds typically when we have an El Nino event, because there's no wind and no nutrients. So El Nino events are on the rise, and we may be experiencing more of those crashes as we move into the future. Okay, OA. What is OA? OA is not the Netflix TV series, okay, of the same name, but it's actually ocean acidification. Let's talk about that. This is a very serious problem for marine animals. Let's go back to the curve that we had. This is a Charles Keeling curve where he measured the carbon dioxide going up and up over time. And in fact, there's the atmospheric carbon dioxide. There's ocean surface carbon dioxide because the ocean is absorbing carbon dioxide out of the air. This is also increasing at the same rate. And ocean pH is going down, which means the acidity is going up, since it's a reverse relationship. So over time, the acidity of the ocean is going up. And that means that more acidic water actually lowers what we call the saturation of calcium carbonate in seawater. Calcium carbonate is basically limestone. So these are in ionic form in the seawater. And the calcium carbonate, the carbonate ions, are the ions that the sea organisms pick up. Anything with a shell, either an external shell or an internal skeleton, needs calcium carbonate to build their shells or their skeletons. So this acidic nature makes it much more difficult for them to extract that limestone or that calcium carbonate out of the water to build their shells. So what's happening here? That's going to affect all those nice things that you like to eat: oysters, scallops, abalone, sea stars, corals. All those things that need calcium carbonate are definitely going to suffer with that process. By the end of this century, it is predicted that the ocean surface temperature will be more acidic than it has been in 400 million years. So we need to solve this problem. So where do we go from here? I don't know. Where do we go from here? Oh, let's go to Paris. Okay. 2015, Paris, the World Climate Summit. That was a time, December 2015, when the Conference of the Parties, COP, Conference of the Parties 21 met. They have a Conference of the Parties every single year at the end of the year. This is the United Nations Framework Convention on Climate Change. And in 2015, there have been, many countries have been working before that to set up an agreement. 194 countries participated in the Conference of the Parties 21, and with a goal to develop an agreement whereby the international community would work together to keep global warming at or below a 2 degrees centigrade or a 3.6 degree Fahrenheit increase beyond the pre-industrial levels, which were about 1800. The Paris Agreement was entered into force a year later, this last fall, on November 4th at COP22 in Marrakesh, Morocco. And all of the countries except two, that wasn't supposed to be there, all except two signed on to the Paris Agreement, and that was Syria and Nicaragua. Syria was in total war, they didn't sign on, and Nicaragua didn't sign on because it didn't feel like the Paris Agreement went far enough, although Nicaragua in the last month has now signed on to the Paris Agreement. And as you probably know, the current administration has indicated it will pull out of the Paris Agreement. We'll see. So this year, COP23, 2017, is going to be held in Bonn, Germany. Tomorrow it starts. Listen up, watch the news, see what's going to happen. So even though it's in Bonn, Germany, it's going to be hosted by Fiji. And this is the Prime Minister of Fiji, Frank Bainimarama, and his comment was, "We're all in the same canoe," which is so true. The United States negotiators, interestingly, are from the US State Department, going to be negotiating the terms of the Paris Agreement at the same time with those other things that you know about. And I've heard reports that the EPA administrator, the Honorable Scott Pruitt, may also attend. This seems to be a little contradictory here. Some of them are negotiating and other ones are trying to stop it. So we'll just have to see what happens. But it starts tomorrow, so keep your eyes and ears open for what kinds of news situation we might have. The goal, we're not sure what the goal is going to be if there's conflicting agendas there. So where does that leave us with respect to how we can get to where we want to be. This is CO2 concentrations from emissions globally. We're looking at temperatures over here, and here's where we are now. If we project from 2017 onto the year 2100, this shaded gray area here is where we'll be if it's business as usual and we don't do anything. Instead, our current policy projections, doing the things that we project into the future that will be better, are looking like right here, we're only going to increase our temperature by about 6 degrees to 7 degrees. If we then go and abide by the pledges that all the countries have put forward with the Paris Agreement, we may only raise our temperature by 4.5 to 5 degrees Fahrenheit. And where we would like to be is down here, below 2 degrees centigrade, where we can actually start reducing the emissions and the temperature that are increasing. So that's where we stand with that. However, there's some new data that I wanted to share with you. This is interesting. This is a plot of, I hate it when it does that. This is the plot of carbon dioxide emissions, as we've been talking about. And this is from 1980 to 2016, just this last year. And there's a few areas, like during the global crises, the US savings and loan crisis, the emissions flattened out. And that was because the world's economy was slowing down. There wasn't as much carbon dioxide being produced from fossil fuels that were producing all these goods. Also, the collapse of the former Soviet Union, things slowed down a little bit, leveled out. And the global financial crisis in 2008 produced even a depression in the global emissions right here. However, we get up to here, 2014, 2015, 2016, it went flat and it actually decreased a small amount. That wouldn't be surprising if the world's economy was slowing down, but it's not. The world's economy is booming at the same time that emissions are leveling out. That's good news. That's really good news. The reason for this is basically that we're using more renewable energy sources. Primarily wind and solar are making the biggest difference, and there's been significant improvements in energy efficiency. So this is something to be happy about. This all just came out this last March. However, that was the good news. The bad news is up here. Here, the red line is the emissions that we just saw. And you can see up here, this little tick here from 1860, about around the Industrial Revolution beginning, up to where we are now, 2016, that flattened out. However, you can also see the concentration in the atmosphere, not the emissions, but the atmosphere are continuing to rise, and they haven't stopped. The difficulty is that the ocean and the land can only absorb about 50% of the emissions that the world is putting out. If we wanted to flatten out this blue curve, we would have to immediately stop 50% of all of our emissions. That's challenging. We can work towards it, but it's really challenging. So unfortunately, that's where we are today. So what are the challenges to reaching the Paris Agreement goals? It's extremely complex. There's technological and physical problems, chemical problems, biological, geopolitical issues. And the current administration is pulling out of a Paris Accord. However, other countries and states and cities and corporations are continuing to support the goals and the approaches of the Paris Accord. That's good. We need education and continued support by world leaders and by the citizens. And the time we need to act is now. This time is critical. We have probably another 20 years or 30 years before things could go into an exponential mode. We need to improve energy use efficiencies. We need to develop new technologies for alternative energy sources and support those through legislation. And we need to transition into alternative energy sources quickly. So I think you all know that California is a leader in environmental issues, especially with respect to global climate change. Assembly Bill 32 in 2006 was passed. The Global Warming Solutions Act established a program to reduce California greenhouse gas emissions to 1990 levels by the year 2020. ambitious program, but it passed and we're doing it. Senate Bill 32, just this last fall, September 2016, was an addendum to the Global Warming Solutions Act, and it goes even further by reducing greenhouse gas emissions to 40% below 1990 levels by the year 2030. Fantastic. We'll see how that goes. 40% of California's emissions are due to the transportation industry, so we need to do something about that. And in fact, Mary Nichols, who's the head of the California Air Resources Board on September 27th, said that California may ban 40% of vehicles fueled by internal combustion engines by the year 2030. That's not so outrageous when you think about China and France and UK are already planning to ban diesel and gas vehicles by 2040. So we're on the path to getting rid of fossil fuel due to transportation. So those are all good things. What can we do to help? We are all stewards of this planet. This is for your kids, their kids, all the other people who are going to follow us, and you kids right there from Mariloma. We need to get off fossil fuels, promote alternative energy sources. And so what are the global solutions to utilizing alternative energy sources? We have many alternatives. We have wind, that's Altamont Pass. We have solar. We have geothermal, currents, tidal, wave energy, hydroelectric, hydrogen fuel cells, ocean thermal energy conversion. All of these are options for us. And in fact, right now we have the capacity to run almost all of our energy needs off of our alternative energy sources. Now, the question is, we have the capacity, we have the technology, do we have the will? What can we do? Locally, personally, eat lower on the food chain. It lowers emissions and reduces deforestation. Reduce, reuse, recycle, everything possible, especially plastics, which are made from fossil fuels. Use EPA's household carbon footprint calculator for your own home. I'm not even sure this is on the EPA website anymore, but you can take a peek. Drive an electric car or a hybrid car, or use alternative transportation. Hitchhike. Turn off all unused lights and appliances in your home. Cindy, where are you? Use a programmable thermostat. Use Energy Star products. They're great. Don't leave your car idling. And remember, local actions have global consequences. Okay, what can we do globally? Critical, reduce our use of fossil fuels. Be vigilant, communicate with your local, state, and national representatives. Help make environmental education mandatory. Contribute in any way you can. You can volunteer, you can continue to be educated, you can donate contributions. And there's lots of organizations around California that you can go to and that are doing great jobs. But the most important thing, vote. Absolutely. Oh, did I say vote? So what's the bottom line here? There's the bottom line. Proof positive of global warming. Thank you very much. So we can turn on the house lights. Up. Turn on the house lights. There we go. Further. So we have time. We have time for some questions, and we've got some mics. Hey, Carol. And there's two people here that will, if you can raise your hand, there's people who will walk around and give you the microphone to ask a question. So you all got all of that. I'm going to give you guys a quiz if you don't raise your hands. Back there, Jeff.
Don.
Yes.
You talked about automobiles, but what role do airplanes play in the environment?
Good question. What role do airplanes play? Airplanes are one of those sticky wickets. We have a problem in trying to devise an energy source to take care of airplanes. That's one of our big challenges. Airplanes contribute not only in the carbon dioxide that they produce, but also in the trails, the trails that they leave, which condense into water vapor, and those also contribute. Water vapor is actually a greenhouse gas, and water vapor also contributes. So they're sort of doubly bad in that sense. We don't have they contribute a lot to global warming because of not only the CO2, but also the I'm not going to say the word, but some of the tracks that they leave in the atmosphere. So, sorry I don't have an answer for that right now, but we're working on it. Yes?
I thank you very much for your presentation. One of the slides that really jumped out at me was the one about the land subsidence in the Central Valley, and I know recently the state passed a law with the acronym SIGMA, and I'm wondering if you could talk about the law, if you know it, and the efforts to implement the rehydrations of the aquifer in the Central Valley.
I don't know SIGMA per se, but there's a very large research group at UC Davis that is actually locating and investigating geologic formations throughout the state that can be recharged with water from various reservoirs and water from extreme events that happen if they can channel that into different locations. So we're working on it. They're working on it. I'm not working on it. There's one right here. Anybody else? Over there? Somebody have a mic? Yes.
I just wanted to thank you for your presentation. I have a comment more than a question. There was a bill before the California State Legislature this year, SB 100, which proposes to convert California's electrical grid to 100% renewable energy by 2045. It passed in the Senate. It did not pass in the Assembly. So I urge you all to call your state representatives and urge them to pass this bill. It will come up for reconsideration in January.
Very good.
Especially your Senate members. Thank you.
Thank you very much.
Okay.
Where are you? Here you are. Sorry.
Can you kind of explain or go into how volcanic activity helps promote a decreasing global temperatures?
Sure. Volcanoes spew out sulfur compounds, and when they mix with the air, they produce sulfate aerosols. And the sulfate aerosols are actually cooling because the sulfate aerosols, when they're in the atmosphere, they reflect the heat of the sun back out to the atmosphere, so it never reaches the ground. And that's how volcanoes are helping to cool the earth. So if you want to get, cooling going, just stimulate some volcanoes to start producing. Okay? Yes. Yes.
How do you see potential tipping points or other factors that aren't included in these models? How do you see that in these overall projections?
How do we deal with tipping points? Well, there are quite a number of scientists who believe that we are approaching some tipping points, that is a threshold above which or beyond which we would see exponential increases in carbon dioxide or greenhouse gases, whatever they are. Some of those are related to methane, and there's certain things called methane clathrates. It's basically frozen methane at the bottom of the ocean. If the ocean warms enough, those frozen methane compounds will start to melt, and they will start coming up through the water table into the surface of the ocean and be distributed to the atmosphere. And since methane is a very strong greenhouse gas, it's probably 20 times more powerful than CO2, that could really send us off the threshold and be a tipping point. The reason that CO2 is more powerful as a greenhouse gas in general is because it lasts so much longer. Methane only lasts maybe a few years, whereas carbon dioxide lasts hundreds of years. So if we stopped all production, all emissions of carbon dioxide now, those carbon dioxide molecules in the atmosphere now would still be there for hundreds of years. So we need to stop now. Even if we stopped everything today, it would still continue on until those dissipate in the future years. So that's one example, the methane clathrates, that could stimulate this tipping point. Plus, there's another one where you have this ocean circulation pattern in the Atlantic Ocean. If we change that ocean circulation pattern, that could cause more heat to be going up into the Arctic and, again, changing the heat balance of the entire Earth. We have any more right here?
What happened to the 350 movement? There was a big movement in the East, in New England, but when we reached 350, then it started going, and we are already far behind, right?
What happened to the 350 parts per million movement?
Was it renamed?
Was it renamed? Unfortunately, yeah, now we have to keep it as low as we can, but we're way past 350, as you know. But those people, those 350.org people, are still very active, and they're kind of leaving 350 behind. They're just trying to pull it down as hard as they can. We have a question over here with somebody with a microphone, too. Go ahead. Oh, there we go.
For an excellent presentation. Do you have any further comments or information on the raising in ocean temperatures and its effect on the rich California kelp forest and its fisheries?
Do we have a comment on California kelp forests and California fisheries? Well, the kelp forests have been declining in certain areas, and that's affecting not only sea otters, but also all of the other species of organisms that live in there as nursery grounds. Fishes, crustaceans, polychaete worms, the entire community lives in there. So yes, they're being affected by changes in the currents, changes in the temperature, and we're all dealing with that as well. Is that?
Is anybody monitoring that?
Yes, people are monitoring that, absolutely. Yes, there's scientific papers coming out all the time. In fact, I just reviewed one to look at the influence of that those kelp forest declines on many species. Yes?
How much difference does it make for people to get solar heating energy in their homes? Is that an important factor?
Sure. I think the question is how long do you have to go before it's economically feasible for each individual household? Solar is obviously dependent on the sun, so if you're living in a forested area, it's probably not going to be very efficient or efficient enough. If you have full solar options all the time, yes, it's going to be feasible. There's new batteries that are coming out. Elon Musk is producing household batteries that can, like capacitors that can store energy for longer periods of time and then use it when you need it. And I think the rate structure is in favor of using solar. We want to do as much solar as we can. And ever since the Paris Accord has been passed, solar energy firms have been going exponential. So I think we're in good shape there. I think we're looking in the right direction. For each individual home, it's going to depend on what your location is, how many rooms you have, how much heating you need, and how much energy you use. So you have to do some calculations there.
Over here.
Yes.
Since so much of the dramatic change seems to be at the poles, I was just curious about the melting of the ice that would expose more land surface, and what about the permafrost situation? How important is that?
It's very important. So the question is, what about permafrost? And as the ice caps and the over Antarctica and the ice caps in any portion of land melt, you have a snow situation which is white and very reflective of the heat coming in from the sun. But if that melts and you get a brown ground, that's more absorptive. So we're going to have more heat absorbed into the earth as a result of that. So that's going to exacerbate the whole situation. In the Antarctic, basically it's going to cause more of the glaciers to melt, which are going down into the ocean, which will then increase the sea level rise as well. So on both poles, we have problems, and on the land as well. Yes?
So I'm a little concerned about the idea that we can graft our fossil fuel lifestyles onto alternative sources like PV and wind and so forth. So in order to mine and refine the metals that will be needed to build all that stuff, we can't do that without fossil fuels. Mining and refining takes huge, huge amounts of energy. And you can only be able to do a little bit of that with PV and windmills.
Well, a good comment. Unfortunately, I don't have data for that. I'm an ecologist. I'm not a mining specialist or a materials specialist. So I think that I rely on the people who tell me that it's feasible, it's doable, and it's going to be economical. So I don't have a good answer for that, but unfortunately, that's the direction we need to go. Yes, it will cost energy. It will take energy to do the mining, but I don't know about the rest of it. Yes?
Are there studies about possible effects of a nuclear exchange, say between us and North Korea?
You want to repeat that again?
Are there studies on the effects of a nuclear exchange between perhaps us and a country like North Korea, who also has a nuclear weapon?
A nuclear exchange, like we're trading one for one, or we're going to get... Pardon?
Fire each other.
Fire at each other. Well, you'd have a lot of radiation around. That's going to affect a lot of people. I mean, that's, it's going to go up into the atmosphere and it's going to circulate around the northern hemisphere. So I'm not sure what you're asking. Relative to climate change. Okay. I don't know that that's going to change climate change much, except it's going to depress the economies in all of the countries that are involved. So you're going to have less productivity because everybody's trying to survive, and global emissions are going to go way down. So that would be a good thing, but otherwise, I wouldn't say it's going to be a good thing. Yes.
So, for our state of California, as we try to influence our policymakers and our committees,
Yes.
do you have a sense of our problems being education, or more on the side of political, finding ways to motivate people politically, or are we really just educationally still way behind?
I'd say both. Both education-wise, California is a very progressive state, so I think the majority of Californians are like-minded in that degree in terms of supporting issues like advancing alternative energy sources, for one thing. The politics of it is complex. It's certainly there. I think I've given you some of the tools that you need to understand the basis behind the scientific aspects of climate change, which is inextricably linked right now to politics, and unfortunately it's become a political football. But California is way ahead of the game. If we can survive and continue to do things that are going to limit the carbon emissions from the state, I mean, we are a leader, and there's many other countries that are leaders as well. So we should just keep pushing, use the tools that you have, and join the groups that we talked about, and I think we can make a big difference out there. Mike, go ahead.
Tom, a comment and a question. The comment is that I always have believed that the importance of this climate change issue for me is because of my children and grandchildren, much like what you stated. But on Fareed Zakaria this morning, he talked about all the different causes of death for people in the world. And he indicated that 9 million people die every year from pollution of air and water. And he used Beijing as an example. And so it's like it isn't really that far out in the future. It's right here, it's right now in terms of the consequences.
Right.
And that was kind of illuminating for me. My question has to do with the United States military forces have identified that climate change is probably the #1 threat to the United States of America. Can you kind of identify why that might be?
Well, it's both because of, I mean, to repeat the question, the U.S. military has identified climate change as the biggest threat. Why is that? A couple reasons. One is, it is. The next reason is that the military, in terms of a military perspective, the military has been upfront in terms of identifying and understanding what the threats are to them. They have to completely revamp the entire military structure to take advantage of or take heed of all of the things that are changing with their various different forces. The Virginia Naval Base is being flooded right now. There was a visit to them not long ago, and their entire base is partly underwater. They have to move that biggest base in the world someplace else, and they don't want to talk about it. They've gotten new, what do you call them, pilings to lift their docks up by calling it a revamp of stability or something. They couldn't use the word climate change, so they have to do this, in other ways. But the military will be affected very, very severely, and they are some of the people who have been already planning for this for the last decade, whereas often many of the rest of the administration has not. So they're in it deep. Got one over here.
Real quick, does fracking have any effect?
Yes, does fracking have an effect? Fracking is also one of those sources of methane that, just like the cow farts and the clam farts, those things, well, methane is abundantly coming out of fracking as well as oil drilling sites. There's a lot of methane being produced by there, and again, methane being a very strong greenhouse gas, that is being affected there. Okay, over here.
So you mentioned during your presentation about El Nino and how it basically shuts down the Ekman spiral and the upwelling that results.
Yeah.
So what impact does climate change exactly have on the oscillation? Does it change the amplitude or like the frequency at which it like oscillates between El Nino and La Nina, or does it favor one side or the other?
So the question is, does climate change change the frequency of oscillations between La Ninas and El Ninos? And we don't have enough data on that right now. Some scientists think that El Ninos are increasing. Other ones think that it's, well, just kind of doing the same. They only happen about once every 5 to 7 years. So we don't have a long enough data set to really be conclusive as to whether that's changing in a single direction or whether it's just being extreme, like the snowpack that we talked about. So we're not there yet. Yes?
Thank you so much for today. It was very informative and really nice to have some of the most up-to-date information, so I really appreciate that. You did mention about local and state action, so I'd like to, if possible, to mention a few things that are happening in this area or statewide. One is to respond to the gentleman's question. I think he may have departed, but 350 Sacramento is right here and very, very active. And in fact, the president of the board is sitting about 1, 2, 3 rows right in front of me. Lori is raising her hand. Thank you. Lori Littman, and I'm Martha Turner. And one of the things that 350 Sacramento did this fall is a wonderful planting project of trees as part of a much larger project, and Lori can fill you in on that. I'm not quite up to speed on that particular project. The other thing, thank you, Tina, for mentioning SB 100. It's really important, really, really important that people support SB 100 and a clean version of SB 100. And the last thing I want to mention is if you're interested in talking about climate and what your finances can do to both either accelerate climate change or to help improve the situation, I'm also on the board of Fossil Free California, and that's the topic we work on.
Thank you. Polly.
I actually have a possibility for some of you Miraloma High School students out there. Cheers to all of you. In a state like California, where we pride ourselves on our environmental action, I'm always appalled when I drive past any Starbucks, any McDonald's, any In-N-Out Burger that has a line of cars with their engines running. For how long? Because people can't get out of their car and walk 20 feet to stand in line. And I think as a research project, if you pick McDonald's and pick Starbucks or In-N-Out and calculate it over a length of time, how cars and what they are producing and extrapolated that by the state of California, we might get our wonderful Governor Jerry Brown and the legislature to do something about it.
Are you saying we should boycott McDonald's? Yes. Hold on. I have one more question. Yes.
My question is just a title, more personal. Did I hear that you had studied at the University of Connecticut?
Yes.
And did you work with Dr. John Milwaukee, who was a ocean ecologist back in the last century?
No, I was there during the last century. But he and I...
1940s, 50s, and 60s when I was a student. And I know he went on to do a lot of research in ocean ecology of the Atlantic Ocean when he was working on when I was a student there.
Yeah, I was there during that century too, but I'm not going to tell you when.
Okay.
Thanks. Yes.
So I have a quick question. Why isn't nuclear energy listed as a renewable energy source?
Good question. Why isn't nuclear listed? I don't list nuclear. I think nuclear is a good possible answer. But I don't think that nuclear is up to the task yet. And the reason I say that is that we don't have a good mechanism to store nuclear waste, in my opinion. We may get there. Right now, radiation from nuclear waste is not transmutable, right? We don't know how to deactivate radioactivity yet. We're kind of like cavemen that looks up at a bird and goes, ooh, ooh, like that. We have no clue how to deactivate it economically. So if we can find a way to do that, that's a good project for you in the next 5 years. That's why. Otherwise, if we can have a safe nuclear system, I think that'll be great. That's a good alternative. Okay, one.
I have a question.
Where are we?
Back here in the AV room. Tom?
Yes.
Okay, so are you familiar with Nikola Tesla, the scientist?
I've heard of him, yeah.
He has what's called the Tesla Tower, and from what I understand, it's really difficult. Is there any way that would help a solution?
I'm not sure. I didn't quite catch your question, but I think at this point, people are leaving, so thank you very much, and we'll see you soon.